Okay, listen. All right. So week 11, lectures, tutorials for all. All right. Week 12, the lectures is for MEC 2404 students. The tutorials is for all. You do the non-Newtonian one. So since you guys not coming for next week's lecture, all right, the CHE, so I propose this Saturday. All right, maybe 9 to 10, 10 to 11, 11 to 12, 9 to 1. All right. I'll give you a short break in between, so you can 9 to 11, 11, 13. This Saturday is what? Today is 8, 9, 10, 11, 12, 9. This 13. All right, settle down, please. All right, if you can find another time in your timetable that fits my timetable also, all right, you can propose. All right, confirm tomorrow. All right, if you cannot find it, you have to do this. Settle down, please. If you cannot find another time, so you talk to your class rep for those doing CHE 2161. All right. If you cannot find another time, then we just do it on Saturday. If you can, you come and discuss with me. All right. Talk to your class rep. Then your class rep talk to me. All right. We can find a time when everybody can do it. All right. As I said, POSSI confirm tomorrow. All right. So as I said, this week's topic is not okay. All right. So with all those conventional topics that in the textbook one we sort of finished. So these are a bit of extra stuff that we add to the bit of non-standard stuff that we add to this unit. Okay. So it's not standard. Not all fluid mechanics course have it. This week we do non-Newtonian. All right. Next week for CHE 2161 is multi-phase. For MEC 2404 is vehicle aerodynamics. All right. So these are extra. It's not in your textbook. Okay. Lecture slides. So for this week's topic and also next week actually, the lecture notes on Clayton, they are mainly like notes. You can read, more like for you to read. Not so much lecture slides. Okay, it's a bit more detailed. Okay, they are available on your Moodle. So by all means read it. Okay, there are 4 files here, and then non-Newtonian flow 1, 2, 3, 4. They are available on Moodle. I have my own. I've also uploaded it on Moodle in my folder. So I'll refer to my own, which is here. Okay, it's available on Moodle also. Okay. Okay, so the reference material, okay, again, you cannot use your textbook. So here there's a book which you can get from the library online that talks a little bit about it also, for non-Newtonian one. Okay, so let's start. Where are we? All right. So for solid mechanics, shear stress is equal to, what's the symbol? I forgot. G. Strain rate for G. Okay, is G, and then this one is the dx on dy. All right, this is like a strain rate. So shear stress, that's your force per unit area. So if you assume you have a block like this, all right, you put a shear stress on here. Okay, the block will deform. The block will deform, something like this. Okay, This is the dy and this is the dx. Okay, this is shear stress. All right. So in solid mechanics, that's called G. All right, that's the what called modulus. Modulus. Shear modulus. Okay. All right. So in fluid mechanics, when you shear something, some fluid, it's not going to just deform and stop. All right, it's going to move. So what we have is shear stress is equal to mu dx dot dy, where this x dot is actually the u. All right. So in fluid mechanics, when you shear something, it will flow. All right. That's why it's flowing, moving u, velocity u. Just now we were just in the linear range, where there's no elastic or breakage or anything. It's just deformed. Get dy. So this one is called the strain. All right. This is a strain in solid mechanics. This one is called a strain rate. All right, because it's a rate x dot here, the rate of strain. Okay, so far. All right. So for Newtonian flow, Newtonian fluid. All right, and up to now, that's what all we've considered. For a particular situation, pipe flow, whatever flow, external flow, and so on, we say the mu is constant. Okay, but at a given temperature, for the simple fluids like water and so on, it is constant. All right, but it may vary with temperature, but this unit you always get the temperature constant. So U is constant. Normally with T is also constant. At T constant. Alright, so at a constant temperature, there's a particular value. Alright, so for non-Newtonian ones is when we have funny behavior in mu. Okay, so mu, put funny. Okay, and there's a lot of funny things happen now. Alright, there's a lot of different types of non-Newtonian fluids. And these ones are mainly all the more complicated fluids. It's not normally not water or air. Complicated means like more molecular, more complicated. So actually, this topic meant more for chemical engineering, but they added this to the whole unit. So okay, mechanical engineering is rarely but sometimes okay, more rare. Chemical engineering more common. All right, because you not just working with water and air. You got water, air, all sorts of other fluids. Normally all the organic fluids with long molecular compounds, all right, long molecular chains, they display all these funny characteristics, right, where the mu is changes and so on. Okay, I think and there's a lot. All right, here, put here, many categories. All right, we'll look at some of the categories today, and then tomorrow we'll look at the pipe flow problems. And then Thursday, then any other things will clear up there. All right, that's on non-Newtonian fluid. Let's see what type of fluid you have. Okay, fluid does not store any stress. Correct. Yeah. All right. So it's the basically the strain rate. Yes. Okay. All right. Right, do you have a question? Yeah? It's okay, huh? Okay. It looks funny, huh? Yeah. Okay. So here got 3 categories. And then under each category got the more depth. We'll mainly look at we mainly focus on the first one. Alright, time independent. Alright, so that apparent viscosity is independent of time, but normally dependent on the shear rate. Okay, so at low shear and high shear, the mu might change. There's also time dependent one, okay, which we only touch on a little bit, and there's also viscoelastic one, which is the word visco means like viscous, elastic. What's elastic? Solid, isn't it? All right. So those behavior like the solid called elastic behavior in the elastic range, no permanent deformation or elastic. Those behave like fluid called visco. So those that behave like in between, sometimes behave like solid, sometimes behave like liquid, and sometimes in between. That's called viscoelastic. So these are the three main categories of fluids, and I said we only talk mainly about the first one in this unit because we only talk about 1 week. Okay, if you want to do whole course or non-Newtonian, then you can go a lot more in depth, but we don't do that here. This is just a flavor of it. Okay. All right. So with with non-Newtonian flow, all right, this is shear stress. This is your du dy or strain. Alpha is alpha. Gamma is gamma. Gamma is strain. Gamma dot is strain rate. Alright, so just now I said strain, now it's strain rate. And mu, well, previously we didn't have this one, and we call that shear stress to mu times this one. Now this one is A because it's apparent only. At a particular situation, at a particular time, at a particular instant, it has a value, but that value may not be constant. So that's why you call it apparent. In that instant, when you shear at a given thing and you measure this, you get a value, and that's your apparent viscosity. But if the fluid is funny, maybe if you continue shearing it, or you shear at different rates, different value of this might give you different value of this one, and so on. Alright, that's why it's only called apparent. And let's see what time-independent fluid is. Okay. Before I forgot this one. This, and how you measure that mu apparent, I'll talk about the fluid later. These are typical measure systems. Alright? These are called viscometers, or rheometers, or, alright? Viscometer is just measure viscosity. Rheometer is to measure actually the rheology, so the more complicated, the behavior of as a function of other parameters. So these are the typical arrangement. First one is you sandwich the fluid in a small gap between two plates. Normally it's a cone. The top one is a conical shape. The bottom one is flat. All right. This is so that you get a uniform value. Why? Because so that you get a uniform value. How to get uniform value? I can't remember. Okay. Okay. All right. So the strain, shear stress. Okay. Mu apparent is equal to this one over this one, and this one is shear stress over du on dy. Okay. So we want to keep this constant, and this one is constant. So when you go up, your y also go up. All right. In this case, your u is equal to omega r for rotating thing. Correct or not? All right. So when your u go up, you increase so that the delta y also increases, so that, all right, the du on dy is approximately constant in cone stroke plate arrangement. Right? Does that make sense? Okay. That's why. Where is it? Here. All right. So this one, when your u go increase, your y also increase. That's why it's that block of fluid is getting bigger as a function of r. That arrangement there. This arrangement quite easy. Alright, there's this gap of fluid, it's a uniform gap on the height. Normally there's air gap there so that there's no effect from the bottom surface, or minimal. And we just worry about the fluid in this gap. So there's a particular omega, so there's a velocity, the u over dy is constant, and then you can work out based on the amount, the torque required to turn it at a particular speed. You can work out can measure the viscosity. All right. Okay. So these are typical systems used for measurement. And okay. So let's see. This one is a summary of the types of fluid. Okay. So shear stress. This one. Need to enable. Okay. So this one, shear stress is this one. Shear rate is either du on dy and equals to this one. So for Newtonian fluid, shear stress is equal to mu du on dy. So you expect this gradient here to be mu. Or not? Okay. For shear thickening, so let's start with the simplest one. Shear thickening, you can see, alright, for shear thickening, the mu, this value increases with either increases with shear stress or increases shear rate. Alright, increases with this one, I'll just put it that way. Okay, so as you try to move faster, the fluid feels heavier, right? Feels thicker. That's shear thickening. As you try to shear it harder, the fluid actually hardens up. Okay, or actually stiffens up. The other opposite is true. Shear thinning. Okay, as mu go down with this one. All right. Okay, and so those are the two. This. In fact, all these are time independent, right? They're not dependent on time. They're only dependent on your shear rate. So if you have a high shear rate, all right, then you your viscosity either increases or decreases. If it's shear thickening, it increases. If it's shear thinning, it decreases. The other one on top is called a Bingham plastic. So that one is funny, yeah. Okay, it's funny because. Okay, so you say, okay, yeah, looks constant. Alright, but the funny thing here is that below a certain shear stress, okay, for Bingham plastic, alright, when the shear stress is below some critical value, behaves like solid. Alright, so below a certain shear rate, it behaves like a solid. Solid means there's a G, means it's behaving like this, equals to G. This one, it's not flowing. Only after a certain shear stress, then it starts flowing. Alright? Okay. So I think our examples coming out, I won't talk about it. I won't talk about the examples first. The plot below is just the gradient of the plot. If you take the derivative of the plot above, you get this one. Alright? So Newtonian fluid, you get a constant value. Shear thickening, as the curve curves upward, the gradient is increasing, and therefore the gradient here is increasing. Shear thinning, as the shear rate increases, the gradient is decreasing, and that's one is decreasing. Bingham plastic should be. Bingham plastic based on that one should be constant. But I think this one is a mistake here. Okay, this one apparent viscosity with shear rate. Actually, this one's funny. It should be constant, but the note with Bingham plastic is should be constant. Is that it doesn't flow below a certain shear stress or certain shear rate, shear stress. All right. This one I don't think it's wrong. It should be straight. Mu constant when the shear stress is above some shear stress critical. Alright? You got it so far? Alright? So these are time independent fluids. Alright? So repeat again, Newtonian shear thickening is when as you increase the shear rate, alright, it actually the apparent viscosity increases. Shear thinning, the apparent viscosity decreases with increasing shear rate. And Bingham plastic, which is the flow, it behaves like Newtonian fluid above a certain shear stress. Below that, it behaves like a solid. Okay. All right. So shear thinning. All right. So typical ones. All right. Paper pulp, dilute suspensions, polymers, solutions, and melts. All right. Shear thinning. The suspended matter or the molecules tend to become aligned with the flow. So as this one, this again is long molecular chains. as you start flowing, as you start increasing the shear stress, the chains all, instead of being wound up with each other, they tend to be straightened out, and therefore makes it easier to flow. All right, the long molecular chains tend to straighten out. All right. With shear thickening, that's the opposite. All right, with highly concentrated such pressure, progressively stronger interaction occurs between the suspension part as the shear rate increases. So in other words, either the molecular bond increases or the long molecular chain starts to tie up to each other, all right, and mess up. So example, starch, concentrated pigment suspension such as paint and ink. Okay, is shear thickening. This one actually, it's in fact they add this to make sure the paint does this one. So when you are painting, you have high shear rates, then the paint actually can flow and apply on. When you stop painting, the paint will actually stick on the wall. That's how it is. Okay. So when you're painting, example here for shear thickening, when you're painting, all right, you have you're up here, and therefore you actually allow the paint to move. All right. Right? No, actually the other way around. Never mind. Please skip that example. Okay. I think later on the example will come back. Yeah. Yeah. Sure. Yeah. Okay. I thought this one is shear thinning. Actually, for paint, it should be shear thinning. All right. For paint, it should be shear thinning. So when you are shearing it at high rates, when you are actually applying it, the viscosity not so high, so your paint brush not so hard to move. When you stop painting, then the shear rates are low, then the viscosity very high, so that it doesn't slide down the wall, it sticks to the wall or the ceiling. All right. So I think for paints, it should be shear thinning. All right. Okay, hang on. Okay, hang on. Oh yeah, hang on here. I think hang on here. Yeah, what is it? What is gamma dot? Yeah, yes. Gamma is just dx dy. Yeah. I think hang on here. That's the reason why I don't write in PowerPoint. Okay, forget that one. Yeah. Okay, I need to kill this one first. Okay. Recording still going on? Okay. All right. Okay. So, okay, wait. All right. Since we're talking about examples, I'll just finish off with the example. All right. Yeah. Okay, I lost all the ink mark. Never mind. All right. So the one I mentioned, all right, veneer plastic. All right, example of veneer plastic, since we're talking about examples now. All right, an example would be like the tomato sauce. All right, so the tomato sauce in the bottle, if you notice, you turn it over, the tomato sauce doesn't flow out, isn't it? All right, so it's because when you turn it over, it's still within this range here. Okay, the shear stress does not exceed the U. So it's still being like a solid inside the bottle. When you shake it hard, when you hit it, then the shear stress increases up to here, then only it starts flowing. All right, so that's an example of that one. Okay. All right, that one. Okay, so this is the simplest law. All right. I better write here lah. Okay, so for time independent, dependent fluid, okay, the simplest model is power law. Okay, so for power law model, all right, so basically just now we saw this one dot. This one is shear stress. We can have it going up like this. We can have it going down like this. We can have it at a constant. So this one is Newtonian. Alright, this one is shear thinning. This one is shear thickening. Shear thinning, shear thick. Okay? Now I won't draw here lah. It's in the picture. Okay, so the power law model is this one, is equal to some constant K, all right, alpha dot to the power n. Okay? This is sloppy. All right, because the actual one, because this has a direction, this also should have a direction by right. Shear stress is equal to K alpha dot to, all right, this one ensures you're in the right direction, because this one, when you square it and so on, the direction might be lost. All right, given let's say n equals to 2, all right, then you lose direction. When you put negative value, square to a positive value, then things will look a bit cunning, isn't it? You are shearing one way, and the strain rate is going the other way, could possibly go the other way. So, by right, this one for the magnitude, alright, and this one for the direction. So that this one and this one are in the same direction. Okay? This is the official way of writing it. Alright, but normally, we just keep this in mind, but normally we just write it this way. Alright? But you must keep in mind that the shear stress and the strain rate are in the same direction. Okay? Otherwise, if you shear this way, the fluid shears this way. Not you shear this way, the fluid is going the other way. Okay? But if example n equals to 2, that is possible, isn't it? Alright, so to take that out of the equation. Alright, so for Newtonian fluid, your K is equal to mu and your N is equal to 1. Okay or not? Is that right? So that therefore this one then it becomes shear stress is equal to mu, which is equal to mu du on dy. Okay? For shear thickening, alright, shear stress is equal to K alpha dot n, and you look at here, alright, the n is more than 1, correct or not? Alright? It's like a parabola or higher, whatever. Alright? So here, shear thickening n larger than 1, shear thinning. Shear thinning, this one's the same, n less than 1. Is that okay? So this is the simplest model. Alright? Remember that this is only a model. Alright? We can measure this one from the rheometer or whatever device that we use. Alright? We can measure that one. But the fluid doesn't know that it's a power law fluid. Alright? It's just we putting that okay, this looks like quite repeatable, quite consistent, it's quite time independent, and this is a curve fit to that one. Alright? So these are, remember, these are just models. In fact, all of them are models. Okay? Fluid model. Alright? So they are just based on the behavior of the fluid. We assume that it behaves like this, and then we try to curve fit and try to find a K at the end. If you get a good value, good nice curve fit, then yeah, it's sort of it's a good fit for the model. If not, then maybe it's the model cannot be used for that particular fluid. All right, so it's just a model curve fit. All right, put curve fit. Okay, save this one. All right. All right, so shear thickening and larger than 1, usually up to 1.2, 1.3. Shear thinning can go down to 0.5, usually between 0.5 to 1, but can go down as low as 0.3 in some cases. Okay, Newtonian 1, no problem. All right, so this is the power law model that we use. All right, there are other models around, okay, but we don't use them, not in this unit. All right, these are more complicated models. Right, to the curve fit. More parameters, more coefficients that can play around. Just to show you that, don't just think that non-Newtonian fluid only has one model. All right, just there are other models. Depending, sometimes the curve sometimes the behavior of the fluid very funny, so it can just a parabolic or power curve cannot fit it. All right. Any questions so far? All right. So, where's my notes? Right here. All right. So right here. Okay. Other models available if power curve cannot fit well to the measured data. What data are you measuring? Data. Example, if your fluid, this is this one, this is this one, the fluid does something like this. Okay? Okay? It got some funny curve, then you need to find another model to fit it. Okay? Not power law. Okay. Okay, I'm just guessing. I don't know whether there are any fluid like that. But in case you have other ones, then there's that possibility. Okay. All right, Bingham plastic. Okay. I'll finish off with this one. All right. So just now I told you this is a bit more officially written here. All right. So if the shear stress is below some critical yield value of Bingham plastic, then it behaves like a solid. This beta. Okay. Okay. Sorry. If the shear stress is below the yield shear stress, then there is no strain rate. Strain rate is 0. It's just there's some deformation, like elastic deformation. If the shear stress is above the yield stress, then you have a minus beta alpha dot, right? Or minus gamma dot. Alright, so this is the equivalent mu one. Alright, this is the equivalent the apparent viscosity. So, and in this one it is constant now, this value of beta. Alright. So I said I already described that one. Anything else? Alright. So other models for yield stress fluids. So again, that one was for That model was a simple one for Bingham Plastic, but again, there's others. Other models, if your Bingham Plastic actually behaves funny, behaves strange. Okay. This one. Okay. Let me finish this one. Alright. So example of time dependent behavior is like this. This is Silly Putty. It's a toy for children to play on. Okay, it's like Play-Doh, but I hope it works out. It's been in my cupboard for a while. At high strain rates, it behaves like a solid. Okay. Alright? So it just breaks off. Okay? Its low strain rates actually can. Alright? So again, I tried at high strain rates. Okay? At low strain rates, it flow like a fluid. Right? So it's a toy. They just don't sell it here only. It's actually very common. I bought it in Singapore. It's very common in the US and all that. It's been around for many decades already. It's called Silly Putty. Okay? So I think next class wants to come in. I'll finish off this one tomorrow together with the pipe flow. Okay? Huh? Yes, with the shear stress below the yield stress, it will act like a solid. Yeah?
I don't do my onions.
Tomorrow.